Now it should be recording, and then I need to share my screen. All right, can you confirm that you see this slide?
Yes.
All right. Okay, thank you. Sorry. So yesterday, just to recap a bit, we reached this point where we were discussing how to evaluate robustness of machine learning models against different kinds of attacks. And the main notion that we have introduced at this point was this idea of security evaluation curves, where you show how the performance of the model decreases as soon as the, let's say, attack strength or the number of changes that the attacker applies to the samples increase. And so as the perturbation size basically is increased, which is parameterized here by this Dmax value, which can also be indicated as epsilon in other cases. But the main idea here is to look at the profile of these curves to understand if they decrease more or less gracefully, because that indicates a different level of robustness in essence for a model. Okay, so that's the main takeaway up to this point. And of course, all this evaluation has to be grounded on a model of the attacker. So having meaningful assumptions on what can be changed, to what extent, and about what the attacker knows about the system. Okay, so that's the main takeaway up to this point, and we will see some examples of these curves later on in the following slides. So here there is a bit of an analysis on what happened on the Android case. So if you remember yesterday, and in particular, this curve here, it relates to an Android malware detector, for which we showed that you can actually decrease the detection rate by, you can drive it to 0 when you modify the malicious file, so the APK, the application file for Android, injecting a given number of objects, okay, 5 to 15 in this case. And now the question is why this attack is so effective against this detector. And this is basically a paper where we try to explain what the algorithm learns. So I'm not going to give you any detail about this picture that you see on the right, but the main finding here was that learning algorithms in this specific case tend to overemphasize few features. And then if the attacker essentially knows that there are some specific permissions or API calls which are given, for instance, a very large negative weight, so they are a strong indication of a benign content, they can just plug this functionality in their file so that it's misclassified as legitimate. So this is one main point here, so that there are a few features which are highly discriminative between classes, and then the algorithm, any machine learning algorithm, as they are, let's say, lazy, they will pick up the easiest correlation they can spot from data to split the classes as requested by the loss function. So that's the main point here. And the other interesting, and this is also part, so this means that essentially these algorithms are very sensitive to changes of few features in this case. We will come back to the idea of the size of this gradient here later on. But essentially, if the function is really sensitive to this change, that's the concept of gradient, right, of derivative. If there is a large sensitivity to such changes, then this is equivalent to have a large vulnerability to the corresponding attacks. And given that, the other interesting point was that even if you use different algorithms, like you can start with an SVM, logistic regression, some other classifiers, even neural nets, they eventually tend to, even if they have different learning problems. So to train them, you start with different loss functions, regularization terms, and so on. The point is that they still find more or less the same set of discriminant features in this case. And then you essentially end up having very similar solutions, very similar decision functions among classifiers, which also explains why if you attack a different model, then the attack also works very well against another one. So this explains why, at least in this specific application, the attacks can transfer across different models. Okay, so that's another interesting finding, I guess. All right, so far we have discussed attacks staged against two class classifiers, where typically the attacker has a malicious class. There are malicious instances that the attacker wants to have misclassified as benign. Okay, so that's the setting that we have been dealing with so far. So in the next following slides, I'm showing you a trivial extension to the multi-class case in the context of this application with this ICAP robot. As I said, this was an example I introduced yesterday, an application example essentially, where you can craft attacks to trick the robot vision system in this case, which is empowered by a deep net, where you just fine-tune the last layer to learn these new object classes. So this is our, let's say, running example here. And now these are the set of objects that the robot is meant to identify. So you have, in this case, this data set has 28 classes. There are 7 main classes of objects, like laundry detergent, plate, the ones that you see here at the bottom. And for each of these main classes, you have 4 subclasses. So you have 4 different laundry detergents, 4 different classes of plate, and so on and so forth. So eventually, you can have either, let's say, 7 classes or 28, depending on how you use these labels. And so here, this is the set of objects that we have. And now the point is, when you consider a multi-class case, a multi-class problem, you know, an error, you can have different kind of goals as an attacker. So it's no longer just possible to say, I have a malicious instance that I want to have misclassified as legitimate. You can have different goals. And in this specific case, you can have what is called error generic attacks, or let's say indiscriminate attacks, where you have an object from the true class. So let's say this is a detergent, okay? But then you're just interested in having this object misclassified as any of the other class. So everything except, let's say, the true class is okay for the attacker. And that's what is called, it's indiscriminate here in the sense that you don't need to specify the target class. Everything is fine except the true class of detergent in this case. So this can be one modality. And then the other kind of attack that you can have is this error specific, which is a bit more restrictive, because this time you want to specify the target class. So I have the image of a detergent, for instance, and I want to have it misclassified as a cup. So the attacker reaches the goal only if this image is classified as a cup. So if you have a detergent misclassified as a sponge, in this case, the attack is not successful, even though the object is misclassified. Okay, so that's the main 2 cases that we have. Indiscriminate, which are in a sense easier to craft, and targeted attacks, which are in a sense more difficult for the attacker. So if we go into the formulation of these attacks, it's basically the same that we have seen before. So you have the output of the classifier, but then you have this other term here on the right, which is used to specify basically the target. So if you now consider indiscriminate evasion attacks or error generic attacks, what you have here, so this is the objective function. So you want to minimize it, right? So K is the true class. So I'm starting from a point here in the blue class. So the true class is blue, and the attacker wants to reduce this score as much as possible. This is exactly the same we have seen before. So you had the malicious class score, and the attacker wanted to decrease this as much as possible. So this is the same stuff. But then what you need to do to actually move in a perpendicular way to the boundary is subtract the competing class, except, of course, the true one. So in this case, this would just quantify the difference between the support that the classifier gives to the blue class minus the one given to the red class, which amounts to following this line perpendicular to the boundary, as you see here in the picture. And then it's basically the same formulation as before. We just tweak a little bit the objective function. What you see here around the point, this is the L2 constraint on the number of changes that you can apply to the initial sample. So here, this distance function is the Euclidean distance between the center of this ball, which is x, so it's the source sample, and x prime, which is the modification that you are seeking for. So something that is misclassified as either green or red, but not classified as blue, because here we are in the indiscriminate case. So the feasible space is just the volume that you have inside of this hypersphere in this case. Okay, so that's the basic extension to the multi-class case for the indiscriminate attack. And similarly, you can have you can define a targeted attack instead, where what you want is to have, in this case, the blue sample misclassified as green. And so in this case, the formulation can be slightly modified. So you still have a difference between two outputs of your classifier, but this time you want to maximize this function, and K here is the target class. So K for me is the green class, because I want to shift the point towards the region of green samples. So if you maximize this function, you are maximizing the score that the classifier gives to this green class, whereas you are decreasing the score of the competing class, which initially is most likely the blue one, right? If the point is correctly classified. So you have again this game between two forces. You're trying to increase the score of one class and decrease the score of another. And this eventually leads the point to follow this path that you see here depicted. Okay, so eventually the best point in this case would be the one that intersects the hypersphere here in the, let's say, core region of the green samples. So this is really a simple extension. So how you could go from two class to multiple class settings. And of course, this would be, let's say, the loss function that you minimize or maximize to optimize the attack. Okay, so this is, in general, this is called the logit difference. If you consider the output of a neural network before the softmax layer. So these are not normalized to be in, to sum up to 1 and be in 0, 1. It's like the score that you are given from an SVM, for instance. So that's the proportional to the distance that the sample has to the hyperplane or something like that. So this is, in general, a function which has no specific constraint on the values. So it's the logit outputs in this case. And you will see that there are attacks that use different functions, but more or less the underlying idea is always the same, that you need to optimize this loss to implement either a targeted or an indiscriminate attack, subject to different constraints on the manipulations. Okay, so now one may say, okay, then how do I compute the derivative of this function? Because when you differentiate the logits, so what you want to do is compute the derivative of the logit with respect to the input point, and this is fairly easy. So in this case, since here we have mostly a linear layer, this would be the weights of this layer times the gradient that you obtain by traversing the network. And this can be obtained essentially by backpropagation as you did during the training process. It's the same functionality. And then in all these modern libraries like PyTorch and TensorFlow, this can be efficiently computed by automatic differentiation. I don't know if you are familiar with the automatic differentiation. Do you know how it works? Can you type yes or no if you know it? Do you know how automatic differentiation work? Can you type yes or no? If you cannot type, just open the mic and speak, please. Okay, so some yes, some no. All right, I can give, let me think. So you know that actually to compute the derivative, you can actually compute it analytically and then code it. Like you write down the code which corresponds to the derivative. This is something I've showed previously. Let me see if I have the slides. Now you should not be able to see anything, but let me share the PowerPoint screen. Okay, now you see the slides in this modality, but in the analytical case, you need to compute the gradient and then implement it. Okay, so for example, yesterday when we discussed this attack, I told you that we needed to do the analytical computation of the gradient. So you compute these equations and then you encode them in some Python functions, for instance. So that's the analytical way of doing it. Then you have numerical differentiation, where what you do is you start from a sample, you query the neighbors, and then you estimate the gradient numerically by estimating the differences of the outputs. Okay, so that's by finite difference, basically. And this is very expensive. Automatic differentiation is another story. And the basic idea is that you can map this network, or in general, this function, as a computational graph. So here you have, imagine that each layer or each atomic function is a node in a computational graph. And what you do in the, at least let's say in the forward mode, but there are different modalities, but in general, the mechanism is simple. When you process the input in the forward step, so I start from my sample X, my image, and then I apply these functions that you see here, first layer, second layer, and so on and so forth. So as soon as the image, let's say, or the data that you have, the tensor that you have, traverses the network in the forward path, what you do is you store the value of the function and its derivative, its partial derivative. Okay, so each node will store basically the partial derivative of the function that it's computing. And then when you ask the library to give you the gradient back, what happens is that starting from the output layer, the gradient that you have computed along the graph will be basically multiplied and accumulated. So this is an implementation of the chain rule. But the trick is that you need to store, each node is not just storing the current value of the function, but also its gradient. So that's the underlying idea. If you think you need more explanations, I think we can devote a couple of slides to this in the future lectures. Otherwise, I mean, there are a lot of references that you can, even Wikipedia, I think, has a good explanation for that. So you can also refer to that. But the thing is that this process is very efficient. So the cost is that of just computing another forward pass, roughly. So this can be really implemented easily. Okay, so let's go back to full screen. And then I think I need to share this again. Is it clearer now?
Yes, but I mean, basically, we used to call the automatic differentiation with the chain rule. I mean, and also knowing that the gradient is stored for each weight in the computational graph. So, I mean, but we just not knew that it was called automatic differentiation.
Oh, okay, I see. Then it's even better. All right, so yeah, that's the name. It's called automatic or algorithmic differentiation as well. That's a synonym. Okay, but that's the mechanism, right, that you have. So basically, in these new Python libraries, you just call the function gradient or backward, and you get the gradient almost for free. So without having any need of computing things by hand, let's say. Okay, so in this case, you know, the gradient can be computed again fairly easily, and this is just an example of how you can manipulate the input data to have it misclassified. So here you have this detergent, which is misclassified as a cup. In this case, you know, you can spot that the image is slightly perturbed because here you look that there are some pixels which are sort of saturated. And so it becomes evident that it could be manipulated. What you see here on top is the Euclidean distance between the manipulated and the source image of this detergent. Okay, so that's just an example here. And what you can also do is bound the perturbation to lie on a specific region of the image. This can be enforced very easily with the formulation that you have here, because this is actually a box constraint. So this means that for each pixel, you can set a lower and an upper bound. in general, this would be something like 0 to 55, right? Because pixels are bounded in this interval. It could be 0, 1 if you rescale images, of course. But you can also set, for instance, let's say you have an image and there is a pixel that I don't want to have modified, which is the value of 10. Then for that specific pixel, I can set the lower bound and the upper bound to 10, which will impose that my solution can only have 10 as the value for that pixel as well. So, and this is exactly what we did here. So for all the points which are outside the mask, we set the lower and the upper bound equal to the original value of the image, whereas what you see here can be manipulated essentially almost without constraint. Okay, so the only pixels that have 0 and 1 as lower and upper bound are those that you see in this rectangular region of the image. In this case, it was just to exemplify that you can actually concentrate the noise in a specific region of the image, which potentially enables you to print, I don't know, a sticker that you can apply to the real world object to see if the attack also works when you actually reacquire the image from the physical world. So that was the main point in this case. All right. Do you have any questions so far? I think we just extended, the two-class basic attack to the multi-class setting, introducing targeted and indiscriminate attacks. So this was the main takeaway from these slides. And then if everything is fine, we can now discuss a bit what happened in 2014, because I think this is like the point in which all this area of adversarial machine learning and machine learning security took a lot of momentum. So since this seminal paper that I'm going to talk about now, there has been a huge number of papers in this area across, until this year. So there is still thousands of papers published every year. So you have basically hundreds every month or something like that. So it's really difficult to keep pace with the literature now, even though I must admit that there is only a small progress in the area. So it seems that the problem is really tough, and perhaps it could not even be, it's not clear if it could be solved at all. So this is something, at least with the current architectures that are used. All right, so what happened in 2014? It happened that this paper was published, and essentially what these authors were aiming to do, and here you have Christian Szegedy from Google Brain, Ilya Sutskever, and Ian Goodfellow, which are probably the most popular ones. So what they wanted to do here was to understand, how robust is the mapping that this network are able to learn. So they were focusing on deep learning, deep neural networks, which reached state-of-the-art performance on tasks like ImageNet classification. And then the question was, well, can we understand at which point, these networks can change their decision? And the original idea that they have was to say, okay, maybe if I start, for instance, as you see here, from the image of a school bus, and then I gradually start to try to morph it to be classified as an ostrich, what they expected is that the network, they were expecting the network to work as the human system. So until you have like the image of a bus, this is consistently classified. And then the decision might be flipped at some point in which they expected, I don't know, the bus to grow some wings, feathers, and so on to look like an ostrich, but really as humans perceive it. So this was their initial expectation, to find something similar to this behavior. But eventually what they discovered, and this is said by Ian Goodfellow in one of his main invited talks, was that surprisingly they found that, perturbing these images just by a little bit was already enough to flip the decision. At the beginning, they even thought this was a sort of bug in the code, because they were looking at the images. They said, okay, this is the same image. It cannot be misclassified as something, completely different with a very high confidence. So this was quite surprising for them. And then they checked again the code and eventually found that the code was actually right. So the experiment was actually working, and this is how they discovered adversarial examples. So let's say by following a different path, they came up to discover also that using gradients in this case to craft this perturbation enables to achieve easy misclassifications for these networks. And while, if you remember what I said yesterday, we came from a different angle because we wanted to test the security of some machine learning models applied in security applications like malware detection and similar things. So while the angle was different, I mean, the solution was eventually the same, that if you craft these perturbations by following the gradient of the model, then you can actually easily evade detection or easily trick the system. How did they formulate the attack? In this case, it's formulated in a slightly different way. So what you have here, this R value, that's the distance. Okay, so this is the perturbation that you apply. So it is actually this mask here that you see here. So this is what you want to find. So it's a perturbation which has a minimum L2 norm. So the size of this perturbation in the L2 norm has to be very small, or has to be the minimum, such that the classification of the original point plus the perturbation is classified as this class L, which is different than the true class that you originally have. Okay, so this f of x, assuming that the image is correctly classified, is going to be the true label. So basically, this is find a minimum perturbation such that the school bus is misclassified as something different, like an ostrich. And then you have here that the perturbed image should still lie in the set of, 0, 1 is the range of valid pixels of valid images. So this is a slightly different perturbation because they aim to minimize the perturbation rather than maximizing the misclassification confidence in a sense. But again, this can be solved by gradient descent, and this was what they did in that paper. So they used this box constrained limited memory BFGS algorithm. It's the L BFGS version of this gradient descent algorithm. And this is how they implement these things. So the main difference...
Sorry, Professor, but
yes,
is it analyzed in the paper by a theoretical point of view? Because, I mean, for me, it's actually surprising knowing the underlying mechanism of the convolutional neural networks. I mean, if we know that there is the convolution and then the pooling, we know that, I mean, some pixels create a sum, a number, which differentiates parts, groups of pixels, and I mean, it's surprising that the almost same group of pixels that we see creates a totally different result in the, I mean, at the end of the day. So it could be interesting to see from a theoretical point of view and not as a mere experimental one.
Mm-hmm. Yeah, so they did a kind of analysis in this sense in the paper. In particular, so let me put it simple. So you have a chain of different layers, right?
Mm-hmm.
What they measure was the Lipschitz constant of each layer, which you can think as a coefficient that works as an amplifier. If it's lower than 1, then you are basically
a contraction. Yeah.
Yes. If it's larger than 1, you are amplifying the noise. And so in this case, what happens with this perturbation is that they are actually amplified across layers, because these Lipschitz constants are all greater than 1, basically.
So I mean, hypothetically, if we were able to keep the constant lower than 1, it could be secure from attacks.
Yes, exactly. And this is what was tried in a ICML paper, International Conference of Machine Learning. It's called, I think, Parsifal networks.
Okay.
So if you look into this paper, they try to exactly do that. But I think it's somewhat untold if the performance is stable, I mean, is acceptable or not. So my suspect is that if you do that, then the generalization accuracy in the absence of noise will basically collapse.
Okay, I see.
So it's
Thanks.
something. So if you want deep nets to work, you have to accept this this issue.
Okay, thank you.
Okay, you're welcome. All right, so that's basically it for this for this for this problem. Well, another issue here is also that you have a huge number of dimensions, and so the more dimensions you have, essentially, the more the attacker is unconstrained in making changes. So you can imagine that if you add more pixels, then you can somehow dilute the amount of noise across different pixels, which makes that less difficult to see for humans. But the quantity of noise, it's essentially not small overall. All right, so what I want to stress a bit here is the difference, because this is something that we will also see later on, between minimum norm or minimum distance attacks and maximum confidence attacks. So in this intriguing properties paper, they use this minimum distance notion. So they want to find the samples which are as close as possible to the decision boundary, but classified as something different. And this is very interesting if you want to study, let's say, the robustness of one classifier. So you're given one model, it's in white box setting, then it's fine, because you may want to see, you know, how far the boundary is from the actual samples. But it's less useful if you consider a security-oriented setting where the goal is to evade the system. In fact, the question would be, why should I stick as an attacker? Should I stick to perform minimum perturbations or imperceptible ones, right? So if you think to this, and we will expand on this problem a little bit later, it should be clear that this is less interesting. So first, because these attacks with minimum perturbations might be easier to detect. So imagine if you just change the decision threshold a little bit, then you can spot them again. And moreover, if the attacker doesn't even have perfect knowledge of the target system, but you are attacking a different model, then it doesn't make sense to stop, you know, right after you cross the boundary. But you should push the perturbation a little bit more inside the target class, such that when you will transfer the attack, when you transfer the attack to the target model, the probability of evading will be larger. Okay, and this is something we already wrote back in time in this paper that I mentioned yesterday. So in case you're interested, you can have a look at that as well. Okay, so I think we will expand more on this notion later on, but this is the main difference between these two, let's say, paradigms for attacks. Here I have, again, an example to clarify why it's easier intuitively to that maximum confidence attacks transfer better to other models. So imagine that you have, this is your target classifier, and this ball that you have here is the constraint on the L2 perturbation with respect to the input sample. So in this case, the minimum distance attack would be this yellow triangle here. So it's something which is misclassified, but it's right after the boundary, right? So it's the minimum distance to the boundary from the black point. The maximum confidence version of the attack would just instead push the sample much farther away within the limits on the perturbation that you set. So this will probably intersect the hypersphere at some point, deeper inside the target class. Now, it should be clear that the second point is should transfer better than the first one, because if you have like two classifiers which are similar but not exactly the same, samples which are crafted, you know, right after the boundary might be classified differently by the other models. Whereas if you have something which is optimized with higher perturbation values, then this should transfer more easily into other models. Does it make sense to you? So you can look at the example here. So when I'm attacking my surrogate model, so this f is an approximation of the true function. I'm crafting one minimum distance attack and a maximum confidence attack. And then I want to test them against the target model, which is a solid line. Then it's clear that this one may not be misclassified with larger probability than the red one, because the boundary may be slightly modified in in the other case. So in general, these maximum confidence attacks transfer better to different models. I don't know if it's clear for you, or do you have any questions on that? Okay, if nobody is speaking, all right, yes. All right, so this was, let's say, a brief on the attacks. And since this 2014 paper, there were really a huge number of papers published. So there is, I think, an exponential trend. We can have a look at that. But there is one researcher, Nicolas Carlini, who is tracking all the papers that appear on arXiv with keyword adversarial examples, and you see that the trend is really exponential. I think we are on the order of thousands of papers every year now. And there has been a huge number of attacks and defenses proposed to solve the problem. And then many of these defenses have shown to be broken by, stronger attacks in a sense, or because the evaluation that were performed in the original papers were faulty. So this is something we will expand more in detail because it's something really important for this field. But essentially, the main ideas behind all these attack variants are always the same. So namely that you compute a gradient and then you try to follow this path to optimize the perturbation. So many of these attacks are really still based on heuristic solutions or based on gradient descent. There is a line of work which is gaining traction nowadays, which is also using formal verification to compute bounds on these, minimum distances to evasion, so minimum bounds on the adversarial robustness of models. But it's still preliminary and working also only for small models. So it doesn't scale up to very large models, and you have also restrictions in the kind of activation functions that are considered. So mostly this is working for deep neural nets with rectified linear units, so with linear activations. All right, but we will discuss this in more details. And just to give you some names, which we discuss later on in this lecture, there is this FGSM algorithm. This is the fast gradient sign method by Goodfellow and others. The Jacobian saliency map attack by Paperno, Carlini and Wagner, and so on. So these are just 3 of the earliest attacks, but there are like more, I think, more than 50 or 20 nowadays among the significant ones. And you'll see many of these. And again, if you're interested in getting to know more about the history and the evolution of these attacks and defenses in the field, you can refer to this survey paper. And here you can also find reference to the very first papers, the very first seminal papers on this topic by Dalvi and Lode and Mick. So here you have already a very, these were focusing on spam filtering, and they were working on evading classifier and retraining on the attacks to gain some robustness, while Lode and Mick was focusing on understanding robustness from a more theoretical viewpoint, so bounds on the number of features that you should change to evade detection or things like that. Okay, I think this is all for this part. Let me check. Okay, so now this question on why adversarial perturbations are imperceptible. I think it's interesting from some perspectives, but the point mostly is that the vulnerability of classification algorithms in this case has been shown to be proportional to the size of the input gradient. So if you take the input gradient, which is the derivative of the output with respect to the inputs, if the gradient is larger, as I said before, you expect larger. So if you take the L2 norm of this vector here, if this is larger, then it means that the function is more sensitive to changes, and so this curve will be steeper. Conversely, if the size of the input gradient is smaller, the function will be smoother here, and then you will cross the decision function later in space. Imagine that this is like the decision function, so when you go below 0, you change class. So it's all related to the notion of sensitivity. This can be shown very easily by doing a linear approximation of the loss function that you optimize for adversarial attacks. And it's also well described in this paper in case you're interested. But that's it, right? So it's really connected to the size of this gradient. And then since the gradient norm scales with the input dimensions. So if you have an L2 norm, for instance, and you increase the dimensionality of the input space, this L2 norm will grow as the square root of the number of dimensions. Then this means that the vulnerability of this network basically increases when you increase the number of dimensions. And this is mostly the reason, I think, why the noise becomes imperceptible. It's because you have so many pixels that you can actually perturb every pixel by a small amount to achieve a misclassification. In fact, if you attack either classifiers which are more regularized or that work on smaller input spaces, the perturbation needed to evade detection is actually more visible. It's easier to spot for humans. But we will also see that this part is not really interesting in the end, because we don't care too much if the perturbation is imperceptible or not in practical applications. We will discuss that in the remainder of the course. It was, let's say, very interesting and very surprisingly to see that you can actually fool networks basically by presenting almost the same image. But then beyond that, if you think more from the perspective of security, the fact that this perturbation is imperceptible to humans or not, it's not really interesting other than that. All right, so if there are no questions, I would like to do a small, let's say, more interactive part. So we have, in the context of an European project, the spin-off of the laboratory that we have at the University of Cagliari has developed a tool which is online. So there is a website where you can connect to, and you can test and evaluate the security of some simple models on a couple of tasks. The tool is implemented using SecML, which is a library we are building in our lab to perform evaluations of learning algorithms. And this contains different attacks, including the one that we mentioned for evasion or adversarial examples, and many others. And so you can have a look at the repository here. I think we will have also a practical session later in the course where you can play with that with some notebooks. So in case then you like it, please start the repository. And so this tool is implemented, is backed up with SecML. And the underlying idea here is the following. So this is something, let's say, from a more practical industrial perspective. So let's say you have a machine learning model, or a company is asking you to evaluate the security or the robustness of this model. You can take this model as input, as well as the data you want to test the model on. And then you can have, as inputs also, you can specify which kind of attack you want to test and which are its parameters. For instance, you can say, I want to modify the malicious samples of this class with this kind of noise, for instance, L2 perturbation in different ranges. Okay, so imagine that now this is your container. For instance, this could be a Docker container, and this could be an API, which you can call. And the output of this container could be or is the security risk level as a numerical value. So this is going to tell you the model is robust to this attack or not, or to what extent this happens. So this is basically the idea that we had in mind when deploying this kind of tool, and what it produces, given these inputs, the inputs that we just described, is what you see here. So it gives you back the security evaluation curve, reporting how the accuracy drops as soon as you increase the amount of perturbation. Okay, so eventually you see what you see here is a security evaluation curve. And we give also a qualitative description of the security level. We say low, medium, or high, depending on whether, if you compute the average value of this curve, if it's between the first third, so if it falls within between 0 and 33%, then the security level is low. If it falls between 33 and 66%, it's the medium security value. Or if it withstands in the first third, so if on average the performance doesn't decrease more than 66%, then you are highly robust. And that's more or less the meaning of this evaluation. And then we can see the demo, but the main intuition here would be to be able to compare different classifiers, not only from the perspective of accuracy on test data that you see here at 0, but also to check, how these curves behave as soon as you increase the perturbation level. For example, here, if you forget about robustness of models, or adversarial robustness in this case, you would see that the model is very, very accurate. The green one is very, very accurate in the absence of perturbation. But there is another one which is less accurate than the first. So ideally, if you run classical or the traditional cross-validation procedures, you would eventually pick up this model on top. But by running the adversarial robustness evaluation, you discover that the green model is actually more accurate at the beginning, but then it's very inaccurate when it goes under attack. So as soon as the data deviates from the original distribution, the source distribution, then the performance of the model drops significantly. And maybe if this is of interest in your application, you could say, okay, then I might prefer, the red model, because this seems to be more robust to perturbations, which are likely to happen during my operation phase, for instance. So that's basically the intuition here. So we would use this analysis to complement classical standard evaluations, or to understand if a model is robust eventually. So let me share the website. I think I have it open. Yeah. Okay, you should be able to see the browser now. And this was developed in the context of this European project named Aloha, which is going to finish next week, hopefully. So here you have the actual demo. So you can pick up some data sets among the most known and used benchmarks. So now we just support MNIST and Fashion MNIST as databases, and two simple models. One is really a simple neural net, the other one is the LeNet network proposed by Jan LeCun. So for instance, let's take this one and start the evaluation. This will produce the security evaluation curve for this model. It's take a while, I think, because this network is a bit larger than the other one. That eventually should display this curve where you have accuracy versus an increasing level of perturbation. You see what you have here. You have the accuracy that decreases as soon as epsilon increases. You may have some exceptions here, but this depends. It's because we are using a simple attack behind, so it's not always very reliable. We should run it for more iterations, but for the sake of having the result in useful time, sometimes it doesn't find adversarial examples where they instead exist. So this is why the curve may grow a bit at some point, but normally this should not happen. So you should have always the curve that goes monotonically, that is monotonically decreasing. Okay, so this is just an artifact of the fact that we simplify the attacks for this web demo. But then you see what happens here is that then you take the average value across this interval of perturbation, and then it's more or less in between. So it falls more or less here, 0.45. So that's the average value, more or less here. And this is, we label it as a medium security level, okay? Then there is something maybe more interesting here. So you can generate one single adversarial example, because remember that this is averaged over, I think, 100 samples in this case, which are also a few. So when you generate one, it just displays what happens for a specific sample in this case. So here you have a 1, which is correctly predicted as 1. When the perturbation is 0, this is still predicted correctly as class 1. And what you see here is 1 plus epsilon, which you can control here, times the perturbation. Now the perturbation is 0 because you have 0 budget for it, right? So then you can increase it to 1%, for instance. And this is the perturbation magnified and then applied to the final sample after scaling it by epsilon. And what you see is that essentially nothing is really changing here because the perturbation is too small. So the score for class 1 in this case is 0.45, and it's basically the same here. Then if you increase epsilon, then you see that things start to change, but this is again still correctly predicted. So this image is still classified as a 1. And then if you again increase it, you know, the support for 1 is still going down. If you put 0.3, then this is misclassified as a 6. But now the perturbation is quite visible in this case. Okay, in this case, I think the attack here is this FGSM, which is a very simple attack, which manipulates all pixels within a given amount, and it just does one iteration. And of course, for the web demo, we lock the fact that you can change it, so you always use the same attack. But the actual container can give you the possibility of selecting different algorithms to craft different adversarial examples, so using different algorithms. Okay, so if you want, you can actually test it. I hope that the server will resist in case. And then I think I can stop here for the first hour. We can have 10-minute break, and then we can continue with the other part of the introduction. Do you have any questions so far? You think it's clear?
I have a curiosity about the example we have just seen, but is it true that few the less degree of freedoms we have, the less probable is that we receive an attack which is not visible? Because I explained that because when we switch the epsilon to 0.3, okay, and then it was misclassified, but it was visible. Instead, in the example of the autobus and the ostrich, it wasn't visible, although I mean maybe the perturbation was even stronger than the one we have set in this example. And is it because the binary images have less degrees of freedom, or I mean, is there another explanation?
No, I think now it's clear. So in this case, the attack is crafted using the L infinity norm. Okay, this is something I didn't tell you because we are introducing the notion later. But here, the thing is that you manipulate every pixel by either plus or minus epsilon. Okay. So that's what the maximum norm does. You have a bound on each pixel, basically, but you can manipulate all of them by, for instance, plus epsilon or minus epsilon. So now if you consider let's say we use the same perturbation budget, maybe epsilon equal to 0.3, okay? If you consider the binary images, these are like 28 by 28, and they have a single channel. So eventually you have 784 pixels.
Yeah.
For ImageNet models, I think you have 224 times 224 times 3. which is about, I think, 1 million pixels or something like that. So it's a much larger input space. And probably, so if you apply the same epsilon, that would be visible in both cases. But what happens for the ImageNet models is that you probably need much smaller epsilon to have a misclassification.
And even if we have, okay, so I mean, it was the same if we have binary images with 1 million pixels, or is it still different from RGB images?
No. I think then.
I mean, so is it the number of parameters of the nature of the input? And I mean, this is the question.
So there is a component which is explicit, and so the thing is that you have a term that controls, let's say, the vulnerability by doing this linear approximation. One is the size of the epsilon, so it's the budget that you have. The other one is the norm of the gradient. Now, inside the gradient, you have the number of dimensions, but also the weights of the network. Mm-hmm. So depending on, so it's easy to see that if you increase the dimensionality, then the vulnerability may increase, but it's less easy to understand. It's more complicated to understand how the architecture of the network impacts the size of the gradient.
Okay.
Makes sense? Because when you compute the gradient, basically you are doing the product of the weights in each layer for when the neuron is active. So that's going to be, a product that, because the inactive neurons will be 0. So the only gradients that survive until the input is the one that is the chain that goes from output to input across active neurons. So yeah. you could study this, but it's more complicated. So the easiest insight, which is given in that paper and in other papers that analyze these things, is that there is a relationship which is clear with the input size, with the dimensionality of the input, but less with the structure of the network. There is even a very old paper where I think where no adversarial was never used as a term, but this is maybe from the 60s or the 70s, where they study sensitivity of these input gradients for neural nets. And I think there is something about I don't remember which is the way, but there are considerations about the number of layers, so how deep you are, and how the networks are, how the layers are wide. So these two factors affect sensitivity in different ways.
Okay.
So this is the most, let's say, useful insights that I remember from the literature. But on the architectural structure of networks, there's not much investigation. And that's to give you an answer. Then I think that is something else to be considered is the fact that typically these networks are over-parameterized, which is, again, if you know about machine learning and the recent theory developments, it's something that contradicts many of the previous, overfitting and regularization issues. And this could also be something that impacts this problem. In a very recent theory paper, what I get from it is that if you are in the over-parameterized regime for a classifier, then essentially adversarial examples cannot be avoided. So that's one claim that you have in this paper.
Okay, and it makes sense.
Yeah, it makes sense because I think that the space of parameters, or in general, the space where you can move, it's so huge that it's very easy to go outside of the distributions in pockets which are classified as different classes.
Okay, thank you very much.
All right, but I mean, this is really an open problem. So this is what I can tell you from the state of the art, but there's no definitive answer on what's the net, let's say, cause for these examples. So that I think there's no still clear understanding 100% of why they exist and how to eliminate them. So we are still in a very early stage.
From a mathematical point of view, I mean, it's interesting that it is still an open problem.
Yeah, exactly. Okay, then I think we can have a short break, 10 minutes, and then we reconvene at 4:15. Okay. Talk you later on. Bye bye. Okay, so welcome back to the machine learning security course. I think I can again share the presentations. Okay, so so far we have discussed, we have done mostly examples of what is called evasion attacks. So in the categorization that we have discussed before, these attacks are those that you see in this top left corner in this table, which are essentially adversarial examples. So in this case, you have a trained model already deployed or served by I don't know, some company, or used by some system in general. And what you want to do as an attacker is to manipulate the test samples to cause some misclassifications. So that's just one of the potential attacks that you can target against machine learning models. And here I just list some other examples, or better, category of attacks that one can experience when the attacker has different goals or can manipulate not only the test data but also the training data. So in particular, throughout the course, you'll see, so now this lecture today and tomorrow will be again on adversarial examples, because this is essentially the category of attacks for which we have the higher number of papers in terms of both attacks and defenses. And then there will be a lecture on poisoning availability here, and this is going to be on Friday. And you will then see backdoor, sponge, and other attacks over the next week. So just to give you a quick intuition on these attacks, beside this one, evasion attacks that we already discussed, if the attacker can also create availability attacks at test time, and this is sponge. This has been called sponge attacks, and this is a very recent paper where the idea is to craft images, or in general input data, in a way that when the neural network processes this input data to classify it, what happens is that it consumes more energy. So this is why it's called sponge. And eventually, if the attacker sends a large number of such samples, in theory, you could create a denial of service. So the model being served might be, I don't know, shut down, or create anyway problems for who is serving the model. Okay, so that's an example of availability by only manipulating test samples. Then there is all this category of privacy violations, for which I have a bunch of slides afterwards, so I'm not going to discuss this at this point. And the same thing is for backdoor poisoning. I just want to quickly mention what is denial of serving poisoning attacks. In this case, what the attacker does is to compromise the training process of the learning algorithm. So typically by injecting poisoning examples into the training data in a way that legitimate samples are misclassified. So this could be something like I compromise a face recognition system such that legitimate users can no longer access it correctly. Okay, so this is an example. And of course, for all of these cases, you can have attackers with different levels of knowledge, as we have discussed in the threat model before. Okay, so this is just to give you the complete overview of the threats that you can have, attacks against machine learning models. So for backdoor attacks, those are a very specific category of attacks for which a huge number of papers have been published. Some of them you see here, but these are just two of the most recent ones. I think there are more than hundreds now. So you see the difference from 2017, from 2021, we already have hundreds of papers just on backdoor attacks. Now, what is a backdoor attack? I try to exemplify the concept here in a simplified conceptual representation. Assume that you have a system that classifies traffic signs. This is just an example where you have stop signs, which are these green dots, and this is a speed limit sign, which is the red dots. Okay, and this is maybe, you can imagine this as a view in the feature space of some deep neural network. Now, the idea of backdoor attacks is that, assuming that the attacker can compromise the training data, and then we'll see why this is possible, in which cases, what may happen is that he may create these images, for instance, of stop signs that have this yellow sticker below the text, as you see here, below the stop text, and assume also that this is labeled as a speed limit. Okay, so what you're doing now is adding a bunch of pictures of stop signs with stickers and tell the neural network before it's trained that these are speed limits. Okay, so then what happens is that when the model is used during operations, so let's say you have a self-driving car with a traffic sign recognition system on board, as soon as the car is presented a stop sign with a sticker in front of it, then this is classified as a speed limit, as you see here in the picture. Okay, so the idea here is to compromise a system to contain a backdoor, so something that an attacker can activate when they want to craft the attack. Now, how is this possible? So the idea behind these attacks is that typically a lot of companies nowadays implicitly, let's say, more or less explicitly outsource the creation of the models. In fact, there are a lot of pre-trained models that you can download from the web, for instance, from open source repositories or things like that. So the assumption of the author, which is very well explained in this paper that you see here, Bad Nets, was that, okay, let's say I'm an attacker. I got a pre-trained model, for instance, trained on ImageNet from the web. As an attacker, I implant the backdoor in the model, and then I release a new version of the model, again, in an open source manner, so that if some companies, use it or it's used in some products, then as an attacker, I can exploit the backdoor if I need it. Okay. And in fact, in this paper, it was also shown that you can implant backdoors in a way that they remain effective even after fine-tuning of some specific models, which was quite interesting. Now, of course, this attack makes sense. So on the one hand, you want to have the stop limits, the stop signs with the stickers misclassify the speed limits, because that's the goal of the attacker. But this, on the other hand, you also want that all the other samples are classified correctly. So you don't want, that the stop signs or the speed limits are misclassified, because otherwise this would be an availability attack. So if the model is compromised on the legitimate samples, then nobody's going to use it. So you want to preserve the accuracy on the untainted data, so on the clean test set, but still you want to add basically a new class, which is misclassified as something desired by the attacker. So this is the main intuition. And this attack is quite effective on neural networks because they have a very high flexibility in fitting the data. Okay, so as you see here, what they tried to do was to conceptualize this phenomenon, namely the fact that if you inject something which is different from the other data points, then the network just fits these samples without creating troubles to the other decision boundary. So the classification function in a different region of the space. And this is possible because such models have a very high capability of and flexibility of fitting the data. Okay, so that's the main intuition behind backdoors. And here again, we will have a lecture on backdoor attacks and defenses next week. Then let's just make some example on the privacy side. Okay, so this is again a completely different setting. So now again, you have a model which is deployed and served, for instance, as an online service. Hypothetically, as an attacker, you can query the model and observe the outputs. So this is, you are just given black box access to the model. There is a nice paper where these authors that you see here, Fredrickson, Somesh Jha, and Ristenpart have developed what they call model inversion attacks. So what you do here is they consider this face recognition system, where this is a user, so that's a training image for this system. And what they've shown is that by observing the score of the classifier on the query images, so images that I present at test time, if I, let's say, if I take a sort of numerical gradient for these images, so let's say you have an image, you send it to the system, and now you discover that the score for this specific class is low. Then you perturb this image in 100 different ways, but you just slight perturb it. You send again these 100 images to the system, and then you pick the one for which the score increased the maximum. If you iterate this process, eventually you'll see that the reconstructed image would have a very high score for the target class. And in this case, they were able to reconstruct fairly well the original images. So as you see here, essentially the identity of the user can be considered revealed in this case. So this is really a privacy violation. Now, this seemed to be new around 2015, maybe new mostly from the technical development of the algorithm, but there were, to my knowledge, a previous work in this area which were published by the biometric community, and they were known under the name of hill climbing attacks, which gives you the idea that you are climbing a function by estimating a numerical gradient in the end. So that's the basic idea behind model inversion attacks. There are other attacks that do not aim to unveil the training data, but rather to steal the model, and these are called model extraction or model stealing attacks. And there is also another attack that is still compromising the privacy or confidentiality of the model, which is called membership inference attack. This one as the following setup. So you have, again, the model is served as an online system, and the attacker can query the model and observe the classification outputs, as you see here. Now, this attack is able to understand if the submitted image to the system, like this image of a car here, was part of the training set used to build the model, which is something that the attacker cannot directly observe, of course. And this is basically possible because when you train, especially deep neural nets, they tend to provide a very high confidence for the correct class and a very low confidence for the other classes on the training points. So let's say it's an artifact of how you train these models. But this, again, is an attack that enables an attacker to discover if a specific, maybe data set is used to train your system. For example, if I take a bunch of images from ImageNet and I observe the prediction of your model for these images, then I may discover that you actually use a pre-trained model from this data set, which unveils a lot of information for the attacker. Besides, compromising the fact that you know if something has been used for training or not. Okay, so this was just to give you a rough overview of the attack surface, or the kind of attacks that you can craft against machine learning. And what I want to emphasize a bit more now is that at some point, so I've been also questioning myself whether all these, huge amount of academic literature makes sense also from a more practical and industrial, let's say, perspective. And the answer is somewhat that is gaining traction. There is a nice paper by Microsoft Research where they conducted a survey using individuals from different companies, mostly, let's say, I think from the research, R&D units from these companies. But the interesting thing is that they show that these guys were aware more or less of attacks against machine learning, and they were able to also enumerate, let's say, the most important ones. And for instance, one of the threats that companies are more, let's say, are more, I don't want to say scared, but they're more worried about is this poisoning attack and model stealing. So those are the two main threats that are considered relevant according to this survey for companies and for industries. The reason is that I think maybe many companies are collecting data sets from not exactly reliable sources to some extent, or they are anyway updating models over time using data that they collect from users, for example. And so the models might be subject to poisoning attacks. And also model stealing is something that is concerned because essentially when you build a model, you put a lot of intellectual property into it. So your knowledge, your data, and then if someone just is able to copy your model and maybe sell a competing service or a concurrent service for half the price, then your business is in trouble. So these are very attacks that are really, let's say, really concern the companies. And so this is something I thought it was useful to point out also here. And another, let's say, other evidence of the fact that the problem is relevant also from a more practical and industrial perspective is the fact that you have now an increasing number of startups which have been founded by venture capitalists. Most of them, let's say, not all of them, but most of them. So the ones that you see here are the ones that I'm aware of. I'm sure there are more out there. And of course, these ones that you see here are also very different from each other. For example, I can tell you that Resistant AI, they started with a goal of achieving AI security in general, but then they are now focusing on the finance sector. So for credit scoring or these kind of applications. Lattice Flow is an European company. There are co-founders from ATH Zurich, from the, let's say, academic side, and they are also like for specific applications, they are testing robustness of machine learning models. For instance, there is one application where you have trains that have a sort of image classifier to detect if there are problems on the rail. And what they're testing is basically testing if the model is robust to rotations, illumination changes, or let's say more practical transformation more realistic transformations that you can have, more realistic kind of noise that you can have in practice, not just LP norms, right? Robust intelligence is mostly focusing on protecting against poisoning attacks, as far as I know. And the other one, so this one, Adversarial AI, I think it's just, it's mostly publishing reports and updates, so that they are still in a very early stage. Okay, but you can check their websites so that you also get an idea of what the panorama is for from the industrial perspective. And there is also, so the third evidence that the problem is relevant, or maybe it's gaining increasing interest, is also that you have this ETSI working group. So this is a standardization body, and they are starting to give guidelines on how to provide certification and standards for robust AI methods. Okay, so of course, all of this is also, let's say, boosted by the fact that the European Union is investing a lot of money, so it's funding a lot of projects on the area of trustworthy AI, which includes robustness as one of the pillars, but there are also others. And so there is, let's say, one push there is a political force and a political strength which is pushing this research field and the development of industrial standards and companies as well. Okay, so this is just to tell you that it's considered a relevant problem, not only from the academic community, but also outside of that. All right, so I want to spend 2 words telling you why these methods are generally vulnerable to attacks. And for that, I will just paraphrase some sentences from Bernard Scholkopf, who is one of the top professors in the area of machine learning. So, of course, we know that all these algorithms, so learning from examples, is generally has generally been devised under the assumption that the training data, so the past data that you collected, is somewhat representative of the cases that you will encounter at test time. So that formally this means that the training and the test data come from the same distribution. So if this is true, then you have all the classical and statistical guarantees on the performance of your model. And modern deep learning techniques have been very successful on those tasks for which we were able basically to match that assumption that you see on top. So for which we collected a lot of data, like labeled images, labeled speech, and so on and so forth. And in these cases, where we basically collected huge amount of data, then we have now systems that work with respect to the past. But the current problem is that you cannot build an actual agent that you can send in the outside world and hope that it will always work correctly. So it's like if you take a self-driving car and you put it outside, at some point you will encounter some of the corner cases which were not properly covered by your training data, and then you're gonna have problems, or at least unreliable decisions from these algorithms. And the interesting thing is that all these adversarial attacks are just the extreme case where you show these failures outside of this IID assumption of this stationarity of training and test distributions. There is also a very recent trend in research, which is pushed by Andrew Ng, who is another professor, another very famous professor, which is more on, they're advocating focusing more on a data-centric approach rather than insisting in improving, the algorithmic part. So what they're saying is to cover these problems, we need to have take care better of the data that we use for training. So essentially, change the training data in a way that it's more representative of what you are going to encounter at test time. So this is what they call data-centric AI, which is, I think, another very important asset towards developing new AI systems. All right, again, so let me just specify why AI safety is also important here. It's not just, why, the reason is not that it's just fun to break these algorithms, but the ultimate goal is that we want to understand the limits of these technologies and improve the current state of the art. So try to develop algorithms which are more robust and more trustworthy than those we have now. And the final goal would be to be able to use them also in safety critical applications, or at least have guarantees that when they are used in such applications, something bad doesn't happen. And I'm talking about self-driving cars, monitoring or controlling nuclear plants, for instance, use them in airplanes or things like that. So for that, you need guarantees. And at the current state of the art, we don't have them. So it's not like you have a machine learning model and you can say this works as a common device. Like if you have, I don't know, something that measures the temperature of a room or a device, you can say, this is guaranteed to work if the temperature is within this range, minus 30 degrees plus 40 degrees, for example. Outside of this temperature, this doesn't work. So for machine learning models, we don't even have this kind of constraints. So we don't even know for which kind of data the decisions can be reliable and for under which other conditions they are not. Okay, it's not, if you have an image, you don't know whether this can be classified reliable or not at the current state of the art I'm talking about. And so knowing when we can trust these decisions is becoming extremely important. So think if you have a Tesla, under which conditions you can trust the autopilot or not. This is something which is not clear, even though a lot of people trust these models, trust this autopilot mechanism. This still is very dangerous, and moreover, all, let's say, the legal aspects give responsibility to the driver. So if you do not have your hands on the wheel while driving, and you have an accident, then you're guilty. It's not the fault of Tesla. Okay, that's my current understanding, at least of the situation. And I don't know if you have ever seen this video here, but here you have a Chinese company named Tencent AI. They were trying to hack Tesla cars in different ways. In this first part of the video, you see that they show in the screen, on the screen there, an image with a fancy color pattern, which activates the wiper of the car, which is instead only assumed to work if it rains, right? So it should only be activated when it rains. So that's the first, let's say, hacking for this car. And in this other one, this is a bit more dangerous because they put essentially a disc on the asphalt, on the concrete, and as soon as the car meets this disc, or you know, the camera looks into it, then the Tesla car changes lane, and this could be something, you know, more dangerous. And that's the disc. And now you'll see that the car will, the autopilot will change lane as soon as this disc is acquired by the camera. Okay, and that's the moment where it changes lane. So again, here it's important to understand when we can trust these algorithms. And so in this case, I'm trying to understand why, you know, the car decided to turn left rather than right, or why this specific piece of code or application is considered malware or not. There is also another important point from the legal perspective, which is that the European Union has stated this GDPR regulation. I think you know that. And within this article, regulation, there is one article specifically which is developed to, which is devoted to machine learning algorithms and the right to explanation. And this basically says that all European citizens should be guaranteed to understand decisions by automated algorithms in a comprehensible form. That's the general statement that they have. Then how to implement this is another story, but at least this enforces machine learning developers to try to open the black box and see, you know, why certain decisions are made. And the rationale, I think, it's quite, it's correct in a sense that if you are not given access, for instance, to a loan, and you're denied a loan from the bank, for instance, you want to know why. And so far, you know, these decisions are automated to some extent, and it's hard to understand whether this happens because maybe your monthly income is not sufficient, or because you live in a certain area of the city, or some other reasons. But all of these are characteristics that might be used in this decision process. But again, how to correlate the outputs to the input is not easy if you use a complex model, especially. And this is what the GDPR states for machine learning. And again, explainability is also important, not only to understand why certain decisions are made, but also to find issues in the development of these algorithms. For instance, to uncover potential dataset biases that you can have during training, in the training data. So maybe you have a face recognition algorithm that works well for men, but it doesn't work well for women. And so this is a discriminative algorithm in a sense, and you may want to patch this issue. You may discover that you have an issue using explainability methods and then patch it using some other techniques, but at least you are aware that you may have a problem. And here I have just a quick example on images, where I show you this method developed by Ribeiro et al., which is called LIME, which was actually one of the first methods for explaining decision of image classifiers, where the idea is just to highlight, you know, the pixels which mostly contribute to specific decisions, which is again somewhat related to the notion of the gradient of the classifier, or I mean, approximated in a different way. But here, for instance, you have ASCII, which is classified as a wolf. Okay, and despite the two, let's say, animals are quite similar, this is misclassified as a wolf. And now if you use this method, LIME, to see why the algorithm has made this error, the explainability method will show you this picture where it only retains the pixels which are most relevant to make this decision. And as you see here, basically all the pixels that are related to the dog disappeared, right? So you are only left with these pixels here in the bottom left corner and bottom right corner. So if you were to give an explanation, can you have an idea why this ASCII is misclassified as a WOF in this case? What do you think? Does anybody has? Okay,
maybe
yes.
because the environment, the wolf is related to the environment in the images.
Yes, more or less. So the complete explanation is that in the training data, the algorithm was provided images of wolves all collected on a snow background. So you have a wolf and the snow in the background, another wolf and snow in the background, and so on and so forth. And so what the algorithm has basically learned was not the concept of a wolf, but the concept of presence of snow. So every time you have snow in the background, any object is typically misclassified as a wolf. So this kind of debugging tool helps you understanding that you may have a bias in the collection of your training set, because in this case, for example, you don't have any image of the wolf on the grass, or on any other kind of background. And then a remedy might be that you expand your dataset collection by considering different backgrounds in this case. But this was just to give you an example of how these tools can be useful to inspect what an algorithm can learn. Okay, I think I skipped another question, which is this one. Is it possible to collect large amount of adversarial examples and train the net? Yes, to be robust. Yeah, basically this is one of the defenses which is mostly used. We will discuss it later on, but in practice, it's the state of the art in a sense, but still the results that you get are not satisfying, especially because if you generate a lot of adversarial examples with large perturbations, then in the end, the accuracy on the clean data drops by a significant amount. So there is this trade-off which is not easy to handle. But we will discuss these aspects more, I think, tomorrow. All right, so as we have seen so far, safety, robustness, and reliability is one of the pillars of trustworthy AI, as well as explainability that you see here. So the fact that we can explain people why certain decisions have been made by the algorithm, but then there are other issues which need to be taken care of. Fairness is about, the fact that we should treat all people, minority groups fairly, so in a fair manner. AI should be inclusive, should be privacy preserving, and should be also accountable. So here it means that if an algorithm creates problem to a human, for instance, so you have a self-driving car killing a pedestrian. Now, who is responsible for that? This should be also something that needs to be debated, and then it's indeed under discussion especially in the European community, but also in the US to some extent. All right, so but basically then what could we do when we have how can we empower the new AI or ML algorithms? Because if this is the standard version that we have, you have data, then you have a classifier making decision and the output. And we know that this can be tricked to some extent by different attacks or by tampering with data and so on and so forth. So for example, there is a line of work in which you can imagine to have a sort of firewall that works along with your classifier and tries to detect anomalous conditions. Okay, so this is like trying to detect whether something weird happened on the data. So this is a potential model, and when this is happening, then you try to ask a human supervisor to give feedback on the decision made by the model to eventually correct it. So this could work to some extent, but there may be, subtler changes which may not be even detected by this component here. So still, it's a very preliminary vision of how you can embed at least humans in the loop of learning. And then another good practice here might be to incorporate security into the process of ML operations. So if you don't know what ML ops is, this is really, let's say, the parallel to what you have in the DevOps setting for software. So when you develop software nowadays, many steps are automated. So you push your code to a repository, and you can also automate processes on top of that. So you can run unit testing, then you can create, do a release of your product or package, and then you can ship these to the consumers directly. So there is a chain of actions that you can automate, for instance, using Git or similar tools. And MLOps is basically aiming to do the same for machine learning. So helping companies to automate the process of development and deploying these models. Because as it works now, you have data engineers or AI scientists, and they are working together to train new models, package, develop, and ship the model to the users. But of course, this is time consuming for them. So what is happening is that big companies, at least, are providing infrastructures like Microsoft Azure. I think Google has something already as well, where you can actually upload a model, and then this can be tested, deployed, and then monitored as it is used by users. So the idea of ML SecOps would be to augment these cycles, so these ML ops, with the security aspect. So you can have, for instance, the implementation of protection mechanisms that you can plug in during model development or training. You can have security testing in place, similarly to what I've showed you before for the security evaluation of models. Imagine that you have a kind of unit test which is executed every time a new model is generated, so that you can measure security against some attacks, and you can say, okay, this is robust against evasion, but not against poisoning, for example. And then if these security checks pass, as well as the accuracy of the model is satisfying, then you can deploy it. And then you can also have security monitoring in place, which means if I'm serving a model as a web server, I might have, imagine a dashboard where you can check if something weird is going on. If some users are querying your model in a weird way or are trying to abuse it, it's something that you can detect in real time and maybe block the IP of the user, or have the model giving wrong answers to them, something like that. So this is, I think, the vision for the next 2, 3, 5 years, maybe. So that's really the trend, which is gaining momentum at this point. All right, so let me conclude this introductory part with a couple of slides more, and then I will leave the word to my colleague, I think, after the break at this point. So here you have, I hope I convinced you that this is like a new branch of machine learning, which started really back in time, but became very popular when the same issues, let's say, have been considered for deep learning models. In particular, there's a book which is called Adversarial Machine Learning from UC Berkeley professors, where you can get the story of the field basically until 2012 and 13, I think, which is previous to all this work on the security of deep networks. But then I think that these two lines, while they started mostly independently from each other, they are now converging to some common goals and good practices. And so there is hope that these fields consolidate more in the future, and we can draw, you know, the same insights that we had from security and cybersecurity applications. We need to make some how can you say, some blending of the two communities, machine learning and computer security. And as I said, this problem is not only a problem that has academic interest, but there is a lot of interest also outside academia, from many stakeholders which use machine learning models for different goals. There has been many many articles published on magazines and websites where they, you know, divulgate science. One specific that I like is this one, Black Box of AI, which was published on Nature. And you see this comment, I think is very interesting. So this director of data science from this company said, if something were to go wrong as a result of setting UK interest rates, she says, the Bank of England cannot say the black box made me do it. So they have to be able to explain what happens. And so opening up this black box of AI is one of the relevant problems that we have, as well as understanding when these algorithms fail, why, and the root cases behind it. Now the question is also why there is so much interest nowadays. It's, let's say, before deep learning models were shown to be vulnerable to these attacks, there was less interest in this field. And the reason was that before deep learning, nothing were really worked well. Like if you take support vector machines, they were not having the amazing performance that we have now on ImageNet, for instance. And now that things seems to really work at an industrial level, so you have, again, models which are deployed in your mobile phones and then for many different other tasks. People are really disappointed that these models, which are very accurate, even more accurate than humans on some tasks, or at least claim to be, can make stupid errors, apparently stupid for us. But we should also remember that humans ourselves, we are biased. So we have our own biases. So it's not a matter of being too surprised that this is a problem. And for this, I can give you a nice example. But now, as I read it, you should immediately tell me the answer. So assume that a bat and a ball together cost $1.10. The bat costs $1 more than the ball. How much does the ball cost? Okay, so that's the question. And I think if you think to the immediate answer that you would give, that's going to be 10 cents. This is the first answer that comes to your mind.
It will be 1.05.
Yeah. It will be $0.05 actually, but it's this is a phenomenon which is well known as a cognitive bias. It's called attribute substitution, and when you're given this information, you try to solve only one of these equations immediately without considering the other one. So that's why if you think fast, then you tend to give a wrong solution because of the biases that you have embedded in your brain. But this is very nicely explained in this book. I don't know if you know it, but this is from Daniel Kahneman, who is the Nobel Prize in economics. And this book explains very well that for some functions, we carry out, fast thinking in the sense that it's like having the autopilot on. You give the first answer that comes to your mind immediately. But if you slow down and think more precisely to a problem and the solution, then you find the correct answer, or you make a better decision in the end. So this is really something that was of interest, of course, in economic theories for decision making, explaining that many managers do wrong decisions because they think fast or when they are tired or these kind of issues. But again, it's a manifestation of the fact that humans can also have biases themselves. So we should not be really surprised that machine learning is so fragile in some respect. All right, so I think I've discussed more or less what I had to say so far. Sorry if it was a bit long. but here is the conclusive part. So and that's the fact that now that in some sense we have increased the functionality of many systems by embedding, machine learning functionalities into them. This increases the attack surface for adversaries. It's like the example of the fridge that I gave yesterday. If you connect the fridge to the internet or to the web in general, then you're exposed to attacks which you never would be exposed otherwise, right? If it's not connected, it cannot be attacked by the internet. And for this reason, safety of machine learning is becoming a prominent topic now, and probably it will be more and more in the future, as well as the other, let's say, trustworthy AI aspects that I mentioned before. All right, if you don't have any more questions now, I would say we can make another break, let's say 10 minutes again, and then my colleague Luca Demetrio will talk about more vertically on evasion attacks. Okay, so let's sync back at 5:10, okay? All right, see you later.
I can.
Okay, then if you started, okay, you can. Yeah, you can introduce yourself and then keep going. Okay.
First, do you see like slides on me?
Yes, I
do you see? Okay. So, welcome everybody. So to this part of the course, my name is Luca Demetrio, and I'm a postdoc here at the University of Cagliari, and I work under the supervision of Professor Biggio. And I'm gonna show you an overview of evasion attacks that Professor Biggio already basically mentioned in the introduction, but we are gonna cover some more technical details about this. So first of all, okay, if this, please, okay, thank you, PowerPoint. So first of all, I think you already saw something like this. So it is basically a timeline of what happened in the past and what's happening right now regarding evasion attacks. So we started with, 2013, with the attack that Professor Biggio mentioned already to you. And then we have these, these avalanche of strategies that have been proposed. And we are gonna cover basically most of the attacks that we are showing you here. And just to mention that these attacks are not like implemented with pure math, but these are like real things that you exploit with some like code. And so we put here also some of the most famous libraries that have been used to produce the attacks that you see here. And this is just like for future reference. And I think you're gonna cover some of them in the experiment in the laboratory at the end of the course. So just to start this very, very long timeline, we go back to 2013, where the idea of using gradients was the key point for attacking a classifier. So you have a model, and it's differentiable, as I think you know by now, and then you want to reach the other class. In this case, if you look here at this point, maybe you are in the red class and you want to go to the blue class, or vice versa, depending on the class you want to travel to. And then what you do, you exploit the notion of gradients. So as you might have been familiar with, a gradient is just a direction where the function has a maximum ascent. So by following that and by choosing choosing a goal, the attacker can shift a point toward the class he wants. In this case, we have like only binary classification, so we have only 0 and 1 as classes. So in 2013, what happened in 2013? So this is basically the first gradient attack that has been proposed, and it has been tested only on the so-called like shallow models, as they call it by now. So only like linear and non-linear classifier with kernels, so not deep learning. And these perturbations were bound with two different norms, the L1 and the L2 norms. And the point of this attack, so one of the intuition of this attack is, well, the starting point of such an optimization might not be good. So I want to find one point inside my space that is very likely to go toward the other class. So in this case, it has been added this kernel density estimator that you can see here, which is basically this summation, this quantity that penalizes points that are very, very, that are like not likely to bring you to the other class because they are in a region of space where there is nothing. You can think you can think it as if k, so this function, if the kernel function that you're using is like the exponential, you can think about like a Gaussian that is imposed on your points. And if you're taking a point on this Gaussian, the density should be higher. If you take something very, very far away, it should be less. So if you don't choose this point if you don't choose this point in a good way, you might end up in a region where it's impossible to find an adversarial example because you go basically into you go in the opposite direction. So to bridge this gap, instead of using like a kernel density estimation, instead of like going too much far away in the future, let me explain a bit more what this algorithm did. So first of all, you take a point somewhere that is like good to reach the other class. Then what you do, you compute a gradient, and the gradient is in telling you have to move along this direction, and then you update your sample, so you'll end up here. Then what you do is, you keep iterating this process until you find what we call the constraint. So what is the constraint? The constraint is the maximum amount of perturbation we want to apply to a point. Intuitively, we don't want to like apply an infinite amount of manipulation because otherwise the sample would be destroyed. Imagine like you have a picture of a dog, and with an infinite manipulation, you end up with a black image. This is not exactly what you want, right? You want the dog to be still there. So what you can do, you constrain such manipulation, and then if you reach this constraint, you just project inside the constraint. So in this case, you basically keep, going back and forth on this circle until the iteration of the algorithm are over. In this case, the sample is considered as adversarial because it's crossed the boundary and it's already inside the other class. The problem of this algorithm is that you have this kernel density estimator plugged inside the optimization. So maybe the attacker might want to get rid of it. To do that, we need to further going on into the future, and we might think about, well, let's find a way for a better initializing points. And instead of starting inside the class you want to be misclassified, you start from the other one. So in this case, you start from the blue class, and then you go through, you go toward the real starting class, and then you find a point into the boundary. So this blue point is basically what we want to reach. Then we go back, we go to the real starting point that is closest to the solution we found by optimizing this problem, and then we do again gradient descent. So what's the pros about doing this is that you don't care anymore about finding like a good point inside the starting class, but you just do what is called an adversarial initialization. So you find something that is already in the class we want to reach, and then we approach it, we move it toward the boundary. If you need like an visual intuition, you can think about like building a bridge from both sides. So you build the first part of the bridge, and then you wait for the other to reach you. And this is how this attack works. And this is how you basically remove the kernel density estimator out from the original attack. But so this was like one line of work. So just working on the like linear and kernel models, but parallelly at some point, as Professor Beach already showed you before in this course, is that someone started to think about how deep learning behaves in these ways. So exactly in 2014, Sajedi et al. Thought about, okay, let's try to explain the classification. I mean, what deep learning, a deep network does. And they basically try to understand what happens if you take a point and then you perturb it by a very, very small amount of noise bounded to an L2 ball. So it's like, Cartesian, it's like the Euclidean distance. And what happens is that they found like these intriguing properties of neural network where the prediction was not robust anymore. And that was, and not only that, they also found that many networks, also basically all of the network they tried, were affected by this strange behavior. So this is not exactly an adversarial attack. It's just like a phenomenon they have observed while trying to understand what they do. And as you can see here, I mean, they take like a bus and they compute this noise, which is very, very, I mean, it's a very strange pattern. And then this bus is misclassified. It's not a bus anymore. But this is something that, I mean, you already know by this introduction. The key point here is that at this point in time, in this parallel branch of research, they were not, I mean, it was not that clear that it was like something that can be, I mean, exploited, because the question was another one. The question was, is how these things works in the, I mean, from the explanation part of the, I mean, of the prediction. So from this point on, they also on this side of research, they were aware that deep learning has some kind of strange behaviors. And that's what happens in 2015. So they basically developed, I mean, most of the authors that were already in that paper also worked on this paper, and they created the so-called fast gradient signing method. So it's another definition of, I mean, this is basically a definition of an attack. So the intuition is that I want to use the gradient. I don't want to go iteratively as we did for the gradient descent with kernel density estimator, but we want to perform one step toward a goal and try to produce a misclassification. So this is just a single step attack. So it's not iterative as we saw. And the perturbation, as you can see, is basically controlled by this parameter epsilon that is multiplied by the sign of the gradient. But how this sign comes from? So to explain this thing, we need to understand how norm works. So, I mean, I think you might be familiar with norms. So now it's just gonna be like a super brief recap to understand how these things works in the context of adversarial attacks. So for instance, the L1 norm is just, I mean, it's just like a box, if you can think about it. It's just like 1, -1, and I mean, on all of the edges. Then you have the L2 norm, which is basically, it's just a ball. And then you have called the L infinity norm, which is the maximum along each of the dimension. So if you have like a unit vector, I mean, you have a vector, normalize it to, I mean, if you ever normalize a vector and you compute the infinity norm, maximum is going to be like 1 in absolute value. So it's a square. So with this in mind, the authors of the FGSM attack thought that they wanted to use the infinity norm because they wanted to introduce a global modification on all the image. And for this reason, the infinity norm does exactly that. If you bound the perturbation with that, you're going to say that all pixels must be at least modified by this epsilon parameter. And to further maximize, I mean, if you maximize this, what you compute is exactly the sign, because you want to produce like the largest manipulation possible. So that's why this sign here is present. And this is basically the concept of the dual norm. So it's basically the thing you need. I mean, if you need to it's just a superior bound of your norm. And in this case, that's why the sign is present in this formulation. So you take your point, you want to bound it with the infinity norm to imprint a global perturbation of the image, and then that's exactly equivalent to computing the sign of the gradient of the loss function, and then multiply it by epsilon. And epsilon basically acts as a scale to this box. So if epsilon is very, very little, your box is gonna be like super infinitesimal. If epsilon is very, very large, this box basically is gonna become huge. So as I was saying before, this is a global perturbation. So think about so if you have like images in the RGB space, and each channel is encoded in like 0, 1, let's say, and you have epsilon 0.5, it means that you are forcing a perturbation of of half of the pixel values on all of the pixels. So this might be like a very, very giant manipulation for your image. In this case, here you can see already there is like some patterns that is visible on the token that is misclassified as an orange and not as an animal anymore. Of course, the smaller epsilon is, the more unnoticeable the manipulation is from a human perspective. For a human perspective. So the point is, this attack as a problem is not iterative. So you just do one step of FGSM and then you're done. And basically, you can see here, like this point is enclosed in this box, and this is FGSM, and you're done. So you might not reach the other class. So what they did in 2017 is that, okay, let's take FGSM and make it iterative, as basically already people did in 2013, but they were not, again, it was like some sort of parallel research at some point. So since here we have the infinity norm, what the attack does is just this very strange, straight path, because again, the infinity norm is a box, and since you move toward the maximum ascent, you for sure go to one of its corner, and then you keep repeat the process until either you find like the boundary or either the constraint, which is again, it's an infinity norm, again an infinity norm constraint, so it's a box, is found. So in this case, after like 3 steps, in this very, very toy example, you find the other class. And this concept is maybe also known as projected gradient descent, because at some point, the people from the Madri lab, and they took their name from, so they basically proposed this attack for other reason, but it was already proposed as this so-called basic iterative method, which is just FGSM, but in an iterative way. And PGD basically became one of the become the state-of-the-art attack for testing the adversarial attacks on models. So if you look at the paper, you're gonna find PGD instead of this beam, which is that's the original one. But the concept is exactly the same. They took the infinity norm, and each step they project the new sample, the updated sample on the box that is centered on the point you're looking at, and you keep repeating until you find an adversarial example. So the point is, how can we improve this? So in general, let's forget about iterative or not iterative. Now we're in a point in time where the manipulations are just unconstrained. So yes, you're constraining with epsilon, but basically you're perturbing all of the image. So the point is, how can we make these more sparse? How can we make the attack more convenient from a perturbation budget? So even if this was proposed a bit earlier in time than by PGD or BIM, we have to think about that in 2016 there was FGSM that was everywhere on the internet, and with picture of pandas that became like a gibbon, and people were a bit concerned about that. So in 2016 they released this deep full attack, and the idea is that we want to reduce the perturbation that we are applying. And we want to forget about the L infinity norm because it's too coarse. So what Musavi and Desfuli et al. Did with Deepful was taking just a linear approximation of the function. So imagine that this is your function, the one you see in the figure, and then you compute the gradients. So instead of like doing norms or sign or whatever, they just compute a linear approximation of the gradient. So by scaling it into using like the normalizing it as the L2 norm, and then moving in that direction. And since the gradient, again, is the direction of maximum ascent, this is orthogonal to the boundary you want to reach. And this, this induces sparsity because you're only moving you're only moving your point by the necessary directions and not all of the directions. And this worked because, as you can see here, this is the perturbation that the Deepful applies to this image, and this is the one that FGSM does. And I think you can see how many black pixels are here that are basically pixels that are untouched by the attack. And here, all of the pixels are for sure modified. Because again, FGSM takes the sign of the gradient. So even if the gradient is, in that entry is like 0.00000001, when you take the sign, this is 1. So you're gonna for sure add a perturbation of epsilon, even if the gradient there was not influential. While if you use Deepful, and basically you're just following, like in all of the giant space, you just follow just one direction, it is possible that many of these directions are 0. So you're not using them all. So again, since we're again in this less is more paradigm, at some point in time, someone said, okay, now we want to do even better. We want just to count how many pixels we're gonna edit. So we don't care about, L2 norm, L infinity norm. We just want to count pixels. In this case, we are using the L0 norm. So the L0 norm is if you have like two quantities, imagine like two vectors that are different from just like 0.1, and then you compute the L0 norm. This is gonna count as 1 because it's one value that differs between them. And this is the same for images. You take two different images and you perturb 1 pixel by a custom amount, and the L0 norm is gonna say 1 because 1 pixel has been modified. Of course, this thing is not differentiable. So what they do is this Jacobian-based saliency map of attack. It's an attack that basically creates a map of each pixel and saying, okay, this pixel is important, this pixel is not, and they basically try to modify only the relevant pixel to the classifier, and then they count how many pixels they are basically modifying, and then they stop after n pixels are perturbed. And of course, this is it's a very, very sparse solution. As you can see here, this like the MNIST, it's a 9 from MNIST, and that is classified as 4. But this is clearly a 9, where basically, a bunch of pixels here have been removed. So this is like it's a very, very sparse attack. And now, we basically, we started from PGD, and we basically understood that we can use gradient. Then we started to reduce the manipulation to make them as unnoticeable as possible. And then at some point, someone thought about, okay, what about trying to defend from this thing? So why we're putting a defense here in the evasion attacks? Because at some point in time, someone wanted to stop, say, okay, now adversarial is done. We have evasions. We just want to patch this and move on, because they thought it was like a easy thing to do. And then what they do is that, okay, since gradient is a problem, let's mask the gradient. And by masking the gradient, let's create some model whose gradient are either 0 or either infinity. And that's how distillation works. So imagine this is your normal trained classifier. Then basically you treat in a way that it becomes like this. So you have this, this step function where the gradient on the flats is 0 because there is no information, and the gradient on the step is infinity. And this is gonna cost you numerical problem. And in this way, the signal of the gradient is completely lost. So in 2016, they say, oh, that's nice. We solved the problem for the adversarial examples, and we are done. But I mean, you know what I'm gonna to tell you, right? I mean, how do you think they might have, solved the problem? That's it's a very tricky question to ask, because the point is that this defense worked in this way. First, they train a classifier that is the normal classifier, and then they train a secondary classifier using the score of the first one in order to make it more like more squared. And basically, this defense is not secure. It's just obfuscating the real signal, but you can reconstruct it. So if you have like a noisy signal like that or a steeper signal, what you can do is just either you can train a model on the same data and substituting it, or either you can just change the loss function that is using. So in this case, what they did, they just removed the softmax layer, that was the last layer, and they just used the logits. The logits were smooth. At some point, they computed gradient descent attacks on it. So this basically started a new tons of research on that, because they understood that this defense was broken, and there were more and people can develop more attack to break the defense that they were published in the years. But it's gonna be covered later on the course. The takeaway point is that in 2016 they understood they did not a good job trying to secure this thing. So how they broke this guy? So these two guys, so Carlini and Wagner, but mostly Carlini, started to reason about new attacks for breaking defenses, and in particular distillation. The first thing, again, as I told you, they removed the softmax. So here, instead of the loss, you have just the function. So these are the output of the pre-last layer. And then what they did is just, I don't care about boxes. I just want an optimizer. I just want a function that can be optimized in all of the way I want using gradients. And the boxes becomes regularizers or penalty terms. In this case, the formulation of the Carlini-Wagner attack is mainly due to this. Is mainly focused on the perturbation that you want to apply. So again, there is the concept of I want to minimize the perturbation as much as possible, but then since you want to cause a misclassification, you need the score of the classifier, but it's modulated by these C parameters. So this C is basically a Lagrangian multiplier. So if you see from a optimization point of view, this is just a constant that modulates how much this quantity is relevant to the optimization problem. So if this C grow a lot, it might take the score of the classifier to a magnitude that hides the norm of the perturbation. So it really acts as a regularizer for the one that are familiar with training classifiers with regularization. Then to further make this attack more effective, they also added this K. K basically modulates how much you want to deep dive inside the target class. So if K is 0, you're just relying on the score of the classifier. If K is is rising, you're basically reducing this score, and hence you're basically moving yourself away from the boundary. So to give you a visual example, this attack is what's called a minimum distance attack, because if you bound the if you're asking for the minimal perturbation, you're asking for a point that is as much as close as the boundary as possible. But since K is greater than 0, what happens is that the sample, after it crosses the boundary, it starts to going even further, because it's just simple math. If you just reduce that function, that score, you need a higher score to arrive here. So it is as this boundary here has been shifted here, where the sample is landed after the adversarial attack. So again, if this C is too large, this red point might have ended up here in this quadrant because, because the attack believed that, the attack needed like a more, let's say, a slightly more push to balance the effect of that K parameter. So the Kalini-Wagner attack basically became exactly one of the state-of-the-art attack, and you find this attack in basically almost every paper in the adversarial domain. So at this point in time, people started to think about, okay, can I do better? Can I remove this C parameter, or can I get rid of this K, or can I do something even more like efficient? Because you have to compute this C. You have to, for each point, you have to understand which is the optimal C that is going to lead you to the boundary of the class you want to reach. So yes, the world started evolving, and in 2019 it happened that they used like another old idea, that is again adversarial initialization, for trying to find the point closest to the boundary. So what they do is they start from the class you want to reach, and then you go to the boundary, and again you apply a minimum distance attack. So the attack that applies like the minimal perturbation to reach that boundary. So it's very, very similar to the attack that is being proposed in 2017. That was like the extension of the gradient descent kernel density estimator attack. So, and this is exactly that. So it's just, again, this meet in the middle. So the good point about this is that you saves a lot of perturbation, because again, if you reach from the other class, you already know the things that you can perturb from that class. And then since the only thing that you can reason with are the sample of the starting point class, you basically climb it to the boundary. And then, you try to stop as close as you can to the point you computed. But that's very similar to the adversarial initialization I told you before. So to still trying to improve these things, they think about, okay, but what if I just wanted to, compute adversarial example from the real class. I don't want to go to the adversarial initialization. I just wish to take like a whatsoever point in my class and arrive to the boundary. So I even want to remove the constraint, and I want to say, okay, this function is robust in this radius for n points. Sorry, it's like, oh gosh, okay, so I missed, that was a mistake. Basically what they want to do is that I don't want to care about the constraint. I just want to find adversarial examples even for each point in this class, and I want to basically estimate how far they are from, on average, from the points of my class. So here, that's why they proposed the so-called DDN attack, which is decoupled direction and norm attack. So instead of fixing the constraint, at each step of the attack, they enlarge the constraint or they shrink the constraint, depending on if they found an adversarial example, or if they still need to find an adversarial example. And in this way, you adapt the constraint that you have to find the closest adversarial example to the point you're starting with. So in this case, you have, like in the case A, you proceed in the adversarial perturbation, and you're not adversarial, so you enlarge the constraint. So you pass from here to here. But at some point, you're going to find the adversarial example. But since you want like the minimal perturbation, you're going to shrink this ball until basically you're going to find something on the boundary. So this attack has been proposed for the Euclidean norms, and that was kind of working. But what happens if you want to do the same thing with a LP norm of choice? For doing that, we have to move like very, very close to us in time. In 2020, we have the so-called fast minimum norm attack, which is basically what I told you before. So again, I enlarge and I shrink the boundary, but I generalize it with the whatsoever LP norm you want to use. So you can use like L0, L1, L2, and even L infinity norm. And then you do exactly the same thing. So you do a step with the gradient, and then you enlarge epsilon or you shrink epsilon. But this time, basically, this attack doesn't even care about initializing the first epsilon. It's just gonna compute it by itself. So it was basically a long way to trying to remove as much as possible from the attacks in order to let the attacker do the least amount of work possible. And we basically landed here, where basically we don't even use the constraint anymore, and we let the attack at some point learn the constraint, if you want to see it that way. So, questions so far about attacks? Curiosity? Can I take like a sip of tea in the middle? Okay, if you're alive, and I hope so, we're gonna briefly discuss what are the effects of different norms on the attack that I basically I showed you. So, I mean, I think you heard me saying like I'm gonna use like the L0, the L2, L1, and infinity norm. And so just to give you another like brief recap, basically what is a norm? The norm is just like a distance. I mean, it's a distance, or sorry, it's just like a way for characterizing like the magnitude of a vector. So if you have x, which is like in this case a point, and and then you compute the LP norm, you're basically summing up all of its element at power p, and then you just do the square of p. And I think you're all familiar with the L2 norm, because it's just it's just the regular norm we use like in linear algebra. But then you want to move far away from this. So you have like the L0 norm, which is, again, it's not convex, it's just like a square, and it's gonna say how many in this case they are gonna count how many non-zero elements are in X. Then you have the L1 norm, which is basically the sum of all of the absolute values. Then you have the L2, again, which is like the sum of all elements, at the power of 2, and then like there is usually, and there is also like the square, but in this case you can also like take the square of this guy and remove it, and you arrive to the L infinity norm, which is basically the component with the maximum value. So why this matters to us while doing attacks? So it's a matter of sparsity. The point is, if I want an adversarial attack to be as parsimonious as possible from the point of view of the perturbation, what I do is I use I would like to use the L0 and the L1 norm. Why? Because imagine that, this is my norm, and this is is my optimization problem, and the intersection is my solution. In this case, it's very likely that I'm gonna hit like one of the edges of the box. So this is like for the L1 norm, and basically this is gonna say that the optimal solution is the vector which has only one component to a value, and the other is 0. So this is like a canonic. Basically, it's like a base. If you move to the L2 norm instead, and you do the same, so you find the tangent of the L2 and your solution, you're gonna find something that lays in the middle, which is like a bit of the first component and a bit of the second component, and this is not sparse. So your vector has not 0, maybe has a very small value for one and a greater value for the second, but these are definitely not 0. And from the manipulation point of view, this is what happens. So if you have like a sparse attack, you're gonna edit few pixels here and there, and you're gonna be happy with it, because your manipulation is as little as possible. Otherwise, if you use the L2 norm, you basically end up with something that maybe you can probably see it, but there are like a lot of pixels here in the dark, and many of them, like many gray ones, are basically inside the digit, and the manipulation is basically kind of all over the image. So if you think about FGSM, that's exactly the case. So you're basically widespreading the perturbation all over the image. While if you want to be as much as conservative as possible, you go to like GSMA, and you just count how many pixels you're editing. And this is basically how sparse the perturbation gets. So this was just like, a small recap on how you should use norms and how norms affect the attacks that you are using. So the point is, now that you have like all of this timeline, I mean, it might be like also a bit messy because you have like FGSM, you have GSMA, you have the Carlini-Wagner, you have PGD. We wish to say, okay, is there a way for categorizing all of these things in a usable framework and understanding the differences in a more precise way? Point is, yes. Everything that I told you so far can be generalized by this minimization problem. So you want to minimize the perturbation, delta, with respect to these two quantities. So one is the score that basically caused the misclassification in the model. And the second is the LP perturbation that you want to apply on your sample. And you can recast all of the attacks that I told you about in this form. And the point is how you solve this guy. So the problem is that it's a Pareto frontier. So you're basically minimizing both things at once, and you might want to move along these frontier to find solutions that are most suited for you. So, for instance, if you want like to have an attack that doesn't care about the perturbation but just care about the loss, you're basically going to land here, because here the perturbation is growing unbounded, but the loss is as minimum as possible, and vice versa. So for instance, if you want to use like the so-called, we call this maximum confidence attack, this attack that put like an hard constraint on the size of the perturbation. So in this case, you're gonna just fix this epsilon here, and you're gonna say, no, I don't want to create samples that are like larger than this. And then you want to optimize the loss. So you can arrive just here, and you can descend from here anymore. And then you minimize basically on this side of the frontier. And this is basically FGSM is and PGD, because they just put a giant box inside your starting point, and they say, okay, you can't go further than this. So another thing you can do is just, no, I don't care about the loss. I just care about finding the minimal solution ever. So I do the so-called minimum distance attack. So I put like a threshold there, and I say, okay, I just want to cause a misclassification here, but I want to try to see where this thing lays, and I start to optimize this guy. And this is basically the form. So I'm basically putting a threshold on the score, and then I just move on this side. Of course, this T can vary, but this is basically the idea. And this happens when you use like the Carlini-Wagner attack, when you discard the C, or the JSMA, or the deep full, and yada yada. But the word is not just here or here, right? I would like to move along all of the things. So that's why we introduced the so-called soft constraint attack, that are basically, you're basically solving this goal. So you take this loss function, and then you use also like the distance as a regularizer, or vice versa, as the Carlini-Wagner attack did. And then by modulating C, you're basically finding points, so adversarial examples and solutions that are good either from the point of view of the confidence, or either from the point of view of the distance that you're minimizing. And that's exactly what the Carlini-Wagner attack does. It finds a solution that lies basically here, not on the edges of this thing. And that's interesting because you're not enforcing nothing. You're just moving freely on this Pareto frontier. And then you can become even more fancy, and you can even add, like, if you want, even more regularizers to change the shape of this thing. And also, maximizing or minimizing goals that you might have that are like not only confidence and score. So to conclude these very, very, giant wrap up on attacks, this is basically a table where you can find like what the attack does from the point of view of the constraints and what the attack does from the point of view of the norm. So here, like for the L0 norm, you have like JSMA and FMN. They are both minimum distance because they try to minimize the perturbation. Then you have like for L1, the gradient descent with kernel density estimator, the Brendel and Belgi attack, and again FMN. And then you have all of the others. So for the L2 norm and minimum distance, you have like deep full and all of these guys here. And then the takeaway point from this table is that what do you need? Do you need like a soft constraint attack? So you go for the Carlini-Wagner attack, and it's gonna take care of both constraints. But then you have the C parameter. Or do I want like the most minimal perturbation ever? Then I try to go with the L0, which is like JSMA, but then things might not working because the L0 is very restrictive as attack because it's just counting how many pixels you want to perturb. Then you might say, okay, no, let's just move to something more tractable. So you might gonna choose like FMN or the over the DDN attack, or just even Carlini-Wagner using C equals 0. Or then maybe you just don't care about minimum distance. You just want to, just want to enlarge the perturbation as much as you can, but you want to find an adversarial example. So you just want to go for a maximum confidence attack. So you're gonna be happy using every gradient descent technique like the gradient descent with kernel density estimator or PGD or even FGSM or its iterative version. So it's really up to you depending on your goals. So this basically is gonna conclude like the part of like gradient based attack. And this is like 3 minutes till 6. I don't think there is like time to deep dive into what else outside gradients. So I would stop here and ask you if you have questions about this part or in general about gradient based attacks.
Sorry, I have a question regarding when you are in the comparison between dense perturbation or sparse perturbation. So
okay.
So
Here.
yeah, if I'm interested in the visuality, like how can if a person can detect the attack, then for us is usually dense evasion attacks are better, because visually to me the dense looks better, even if there are some patterns, but they are not as in intensity as visible at the sparse evasion attack.
So you're okay. So thank you for the question, by the way. So the point is, it depends on the perturbation, on the budget, on the perturbation, so on that epsilon parameter. Of course, these are just for pixels, and I think this is just 28 per 28. So even if you just perturb one, you are gonna like visually see it. So for comment this question, I would go back to the deep full attack. So here, I don't know if it's noticeable, but the FGSM attack, as you can see, is basically putting like a lot of salt and noise. Salt and pepper noise, if you're familiar with, while deep full is not. So, of course, if you decrease epsilon, even for the FGSM attack, you might end up with something like this. But if you use a sparse attack, I think it's gonna be it's going to be more effective from the perception point of view. But on the contrary, if you use a sparse attack, you might end up with attacks that are not as strong as the other ones, because you are basically constraining the manipulation to use the fewest amount of manipulations as possible, and that might not take you to the other class. So it's a trade-off again between. It's basically, the problem I showed you in the Pareto frontier. Maybe you need to enlarge the manipulation enough to find adversarial example, and that's the trade-off. So I hope that the question is both, but again, depending on what you want to minimize.
Yes, I understand. For me, I thought because we are decreasing the area, so the intensity of the perturbation is higher. But it seems not only higher, but also the attack success rate is also can be lower.
Yes. So if you use a sparse attack, is this guy here?
Yeah.
So the point is, imagine imagine that you take this epsilon and you just put it on the far more left of the plot, and then you basically you're asking for a very you're fixing the bound very, very low, and then you try to to optimize this guy on this side. So you might not end up with something that is functional to you. Otherwise, if you just take this epsilon and just put it far away, you're gonna find something that is visible, like it's an artifact, but it's evading. So I think it's just a matter of how low you put epsilon for for a maximum confidence.
Maybe if I can jump in, because I think we are
Yes.
also running out of time. Sorry. I think for this question on perception is quite debatable, right? So in general, maybe using dense attacks helps being a bit stealthier to the human system. But again, this really depends on the kind of application. However, there are a bunch of attack papers where they try to, instead of using LP norms, they try to use other perturbation metrics, where the goal is actually to align the perturbation with human perception of noise. There have been attempts in devising such metrics in the literature. So if you go into the literature of signal processing, you find some of these metrics, even though they were not very successful in the end. But there are a bunch of attacks that are aiming to align with human perception in a sense. And you can also check, if you want, Wasserstein attacks, which are based on the theory of optimal transport. And these are, let's say, less perceptible than LP norm attacks in general. But I think it's an open question whether it's worth focusing on this kind of topic in the end. Just because the system is typically not supervised by a human. If you think to a self-driving car and there's a problem of pedestrian recognition, you don't have the material time to ask the human intervention, right? You have to decide whether to brake or not to make a safety critical decision, and there's no time to ask the human to provide feedback in this case. So in many cases, when these decisions have to be really automated and taken in fraction of seconds, then the fact that the attack is perceptible or not from the human perspective is not really a problem. All right.
Yeah, definitely. Thank you. Thank you both.
Okay. If there are no other questions, I think we can say goodbye to the students, and we meet again tomorrow. The plan is to keep going with this attack part covered by Luca, and then we will also maybe start discussing defenses either tomorrow or on Friday. All right.
Yes.
Okay. Thank you, everybody. See you tomorrow.
I'm gonna stop the recording. Okay.